welcome to RF transceiver design course. We are on module 8 lecture 42. Up to now we have discussed the low noise amplifier, which is a first block of receiver design. Now we will move to the next block, which is very important for receiver design, that is a mixer, where we down convert our signal to the baseband. So, before going to the mixer design, we will see the we will try to revise while discussing the RF transceiver architecture. We have already discussed about the low noise amplifier, and now we are moving to the mixer, which is very important component for RF receiver design. So, for RF transceiver design, even in the transmitter we are using a mixer. So, if we see the mixer fundamentals, that here there is a RF signal spectrum. So, the RF signal spectrum which is given here, which is a the signal spectrum is unsymmetrical. So, that we have seen in while discussing the RF receiver architecture, we have seen that if there is a amplitude and frequency both modulation is there, then there is a change in the amplitude. So, your signal will not have a symmetry. So, here a typical RF spectrum centers around a carrier frequency of Fc. So, this is a carrier frequency Fc, around that it is centered, and you can see that how it is shown here, it is a unsymmetric. So, asymmetry in practical RF signals. So, same thing. So, practical RF signals often deviates from the symmetry with respect to the carrier frequency. So, what will happen that when you try to down convert, means what you need to do is you are going to multiply with the e raised to minus j omega naught t or 2 pi f naught t, where the your carrier signal is lying at a f naught. So, in this case your frequency shifting when signal is multiplied by this e raised to minus 2 j pi f naught, it undergoes the frequency shift to the left. So, you can see that here this f c minus f naught and minus f c minus f naught. So, same thing here what we are doing is multiplying. So, we are going to use a mixer for a multiplication. Now, there is a intermediate frequency IF, which is a combination of the carrier frequency and the f naught. So, it is also called the LO frequency. One of the challenge here while designing the receiver, that how can we realize this complex number. So, it is while discussing the receiver architecture, the same thing we have discussed, that how can you realize the e raised to minus j 2 pi f naught t or e raised to minus j omega naught t. So, that we have already seen that if you have a cos omega naught t, that you can represent it here, that is a cos omega naught t, and then if you multiply with j a sin omega, if you add with j a sin omega naught t, your there is a shift in the frequency, and amplitude real part and imaginary part will multiplied with the j, and finally this you will get a single tone a e raised to minus j omega naught t. So, this is how we can generate the e raised to minus j omega naught t. For that what we need is we need to have a quadrature signal. So, this is a I, this is in phase, and this is a quadrature, and then we use a Hilbert transform as discussed to get the down converted signal. So, here what is the challenge? Challenge is in realizing the frequency shifting for RF signal. It is a practical perspective, that introduction to the frequency shifting challenge, the main is a practical realization of the non-real signal e raised to minus j omega naught t So, that you can realize as we have discussed in the last slide. Now, we can use a Euler identity transform. So, same thing, it is called when we are using a combination of cos and sin, it is nothing but a Euler identity transformation to address the non-real nature of e raised to minus j 2 pi f naught t, and it is introduced by breaking down the shifting signal into real component cos 2 pi f naught t and sin 2 pi f naught t, and multiplication with sine and cosine function that we will see in the next slide, and that will help us to get either the upper side band or the lower side band, that we already discussed. If you do the addition and subtraction, you can either get the upper side band signal and the lower side band signal, and the resulting signal consists of two impulses at plus or minus f naught with half of the magnitude. So, same thing here, if you multiply with a cos 2 pi f naught t, it is a half, means half of the portion on the f naught and half is on the minus f naught. So, if you when you multiply, that means it is a convol here in the frequency domain. So, this f c and f c and f naught, f c minus f naught. So, when f c minus f naught is there, you will get this signal. When f c plus f naught is there, you will get this signal. Minus f naught plus f c, you will get this signal, minus f naught plus f c, and minus f naught minus f c, you will get this signal. So, this is how you will get the 4 signal. Out of that, you are interested only on the either means this f c minus f naught. This higher frequency signal we can filter out. So, around DC, a folded replica you can see of the shifted RF spectrum forms a mirror image. So, there is a mirror image that we can see, and f c minus f naught is a small compared to the signal bandwidth, and then two replicas overlap and become indistinguishable. So, what is the solution? In phase and quadrature approach. So, we use a cosine and sine. So, when you multiply with the sine, we will get a plus means f naught as a plus j by 2 and amplitude, and f plus f naught as a minus j by 2 amplitude. Here when we multiply with sine 2 pi f naught t, we have already seen that you can decompose into plus at minus f naught plus j by 2 and at f naught minus j by 2. And now if you try to find out the as we have discussed that I plus j q, if you do the Hilbert transform for symmetric frequency shifting, what you can get is the either upper sideband and the lower sideband. So, what is the Hilbert transform? Multiplies the positive frequency. So, it is like this. There is a this is a plus j and minus j. So, it is multiplying positive frequency component with the minus j and negative with the plus j. So, this will when we do the Hilbert transform, we can reject the image, or otherwise if you use a addition at the output. So, we have already seen that how we have done. This is 2 mixer. So, here we have multiply with sin omega LOT, and then we have multiply with cos omega LOT, and at output there is a 90-degree phase shift, and either you can add or. So, this is a add or subtract. So, if you do the addition, it will have a high frequency side of the shifted spectrum, and if you do the subtraction, you can use a low frequency side. So, any one of them will be the image. So, we already know that in the image reject receiver, this is your omega RF, if this is your desired frequency, and then there is omega LO, then the image will be here. So, that is omega IM. So, this is a image, and this is called a lower sideband in this case, and this is a upper sideband, and here the LO injection is high because this is your RF frequency. So, your LO frequency higher compared to the RF frequency, and there is a low side LO injection, where if you consider this on this side upper sideband as a signal and the lower sideband as a image. So, based on that you can tap from anywhere, you can get both upper sideband and lower sideband. So, the important thing is a multiplier or mixer, how we are going to design a mixer. So, what is a mixer basic operation? We have seen all the basic theory that why we required a mixer. It is required even in direct conversion receiver, and it can also be used in a image reject receiver, where heterodyne receiver or low IF receiver, in all the receiver where we are doing the frequency translation. So, the basic aim of the mixer design is a frequency translation. What it will do is a RF frequency to the IF frequency or baseband, and for transmitter it is a baseband IF to the RF frequency. So, in the one of the case it is a down conversion, and in one of the case it is a up conversion. So, it is using a creative use of a non-linearity or a time variance. So, what is the time variance? We already have discussed while we discuss linearity LTI system. So, in the time variant system, if let us say if I will try to draw it here, this is our switch. If this is your input, if this input is Vx2 t, and this is a switch controlled by Vx1 t, and there is a V out. So, in this case there is a two input, and what is the time variance or time invariance can be given by a when there is a yt. So, in time shifting in input result in the time shifting in the output. So, yt for time invariant system, yt which is equal to this function xt, and if it is a time invariant yt minus tau which is equal to function xt minus tau. So, here when you consider the Vx one is if our interest is Vx1. So, if we consider Vx1 as a input and V out in comparison with the Vx1, then the system is a non-linear. So, if we consider Vx1 as a input to V out, then what we get is our system is a non-linear, and it is a time variant. But if we consider Vx2t, then what is happening, that when there is a switch is on and off, you are getting a Vx2t. So, if you try to increase the amplitude of Vx2t, only the difference is it is considering the output when Vx1 is on, and when it is off it is not, you are not getting any output. But if you change the amplitude of Vx1, similarly you will see the V out also will change amplitude. So, in that case you have a linear and time variant system. So, that is a linear and time variant system. So, mixer, so this is a mixer, we if you use a switch and switch the input with the LO frequency. So, we can say that mixer can be a linear, but it is a time variant. So, there is a one thing is a time variance that will provide the mixing, and another is a non-linearity. So, non-linearity how it's work. So, if your output y is equal to ax a1x plus a2x square plus a3x cube. Now, if this is a yt and if this is xt, so what you will get is a, if your xt is combination of a cos omega rft plus a cos omega LOT. So, if two signals are there, cos omega RF and cos omega LO, when you square the term, you will get the combination of a cos omega RFT multiply by a cos omega LOT, and you will get both omega RF plus omega LO, omega RF minus omega LO, and if you filtered out, you will get the desired omega RF minus omega LO or omega RF plus omega LO. So, that is why what here it is mentioned is, it is a creative use of non-linearity or a time variance. So, how you are going to use a different non-linear device. So, always when you try to design a mixer, you need to use a non-linear device, or if you are switching, it is a time variance. So, this is how the basic mixer can be think of, and it is used together with appropriate filtering. So, we need to use a appropriate filtering in order to filter out either up converted signal or the down converted signal. So, ideal mixer, same thing, if you use a sin omega 1 t, so that is a xt here, and then yt, which is a b cos omega 2 t, which is a LO signal. So, what if you multiply xt yt, you will get ab by 2 cos omega 1 minus omega 2 t, ab by 2 cos omega 1 plus omega 2 t, and you will get a omega 1 minus omega 2 and omega 1 plus omega 2. Here in this, it is considered as a ideal mixer, and other harmonics of omega 1 and omega 2 are suppressed, and there is a no harmonics. So, if you want to use this mixer as a up converter mixer, then you can filter out this, or if you want to use as a down converter, then you can filter out this. So, that is why filtering in combination with the non-linear or time variance is important. So, same thing, mixer behavior in a square load device. So, here a MOSFET is a square load device, and we all know that what is the ID of MOSFET? It is a K into VGS minus VT whole square. So, here what is the VG? Your VGS, if we want to write a VGS, that is VG minus VS. VG is here A2 cos omega 2 t, and Vs A1 cos omega 1 t, and if you try to do the square of this A2 minus, and if you consider omega t as a constant threshold voltage, if you square this term, you will get a k a2 cos square omega 2 t minus 2 a1 a2 cos omega 1 t cos omega 2 t plus a2 square cos omega 1 t. So, this is going to generate a high frequency component. So, you can neglect this, and then you will get a this component which is important, cos omega 1 t and cos omega 2 t, that will generate a omega 1 minus omega 2 and omega 1 plus omega 2. So, how you can also use a square law device. So, this is called a even we can use a diode to do this, and LO amplitude dependence. So, here what will happen, that your mixer gain can depend on the amplitude of the LO signal, which is undesirable in some cases. So, we need to do the proper design of a LO port, can eliminate this amplitude dependence. Switching operation of the mixer. So, now if we have seen the square law devices and how it can, based on the non-linear, it is a non-linear device, how we can use it as a mixer. Now, if there is a switch, if we implement, and this is a VRFT, this is the input, and this is a VLOT, and that is a square applied, and this is a resistor. So, because this switch can replace with the MOSFET, we can write a square wave VLOT as a Fourier function up to the phi omega LO, that is given by 4 by pi cos omega LOT minus 1 third cos 3 omega LOT plus 1 by phi cos 5 omega LOT. So, now what you need is a multiplying with the VRF, that is a RF cos omega RF t. So, because it is a switching, you can write a VIFT, that is the intermediate frequency, and that is equal to VRFT into VLOT, which is a VIFT. So, if you multiply it with this, you will get a 2 by, if you consider the only the first harmonic omega LOT, if you neglect 3 omega LO and 5 omega LO. So, here for first cos omega LO minus omega RFT plus 1 third cos 3 omega LO minus omega RFT, and the amplitude is multiplied with 2 by pi. Now, here one thing to note it down, that if you have this square wave, you will get the multiple harmonic frequency, and that amplitude will be reduced, but you also need to consider that this should be filtered out, and if it is not filtered out, it can cause the distortion in the upcoming stage of the receiver. And one more thing just I want to add here, that mixer is a 3-port device. It has a RF input, LO input and IF output. So, 2 frequency is the input and 1 frequency is the output. So, it is a 3-port device that is widely used in the receiver design. So, types of mixer, as if we summarize based on a square law device and based on the switching. So, we can use a also diode. So, if you multiply the VRFT, if you use a diplexer and use a VRFT and VLOT to combine and give to the diode, and then if you considered only the down converted omega RF minus omega LOT, and that is done by using a IF filter, you will get the final output. There is another way also to do the same thing by based on the switching, you consider the RF input, and RF, you convert RF input voltage to the current. So, what is the basic device that will convert the RF input to the voltage to the current? It is obvious, that is a MOSFET. You can use a MOSFET, and then we need to switch this RF current. So, whatever incoming signal is there, which is a converted to the current, now that current is a switch by using the LO. And that LO, how we can represent, again we can use a MOSFET which can do the switching. We can also use a BJT for the same. So, here you are switching the RF current. So, this is a RF input, this is LO input, and then again we need to convert the current to the voltage. What is the basic component that will generate the current to voltage? It is a resistor. So, we use a resistor. So, this is a very basic configuration of the mixer, where the RF and LO means RF signal is converted to the current, current is switched by LO, and you will get the VIF here. So, this is a two way we can do the mixing, and that will provide the mixer output. Now, we will try to see the various parameters of mixer. One of the basic parameter of mixer is the noise figure. So, while seeing the mixer noise figure, if you draw the thermal noise for the entire frequency, that, and if you show the thermal noise which is spreaded over the frequency bands, and there is a signal, this is a signal band and this is a image band. So, if your omega LO is this, and if there is a image, there is a noise, that will also down converted here, and the thermal noise of the signal is also down converted at IF. So, the single sideband, so if you consider the single sideband noise figure, it is a high compared to the double sideband noise figure. So, in double sideband noise figure, what will happen, that omega LO is centered omega at the same input, that is we are giving omega RF, and then when it is a down converted, the same thermal noise will be down converted. So, your single sideband noise figure is a twice than 3 dB more than double sideband noise figure. So, based on the, either you are using a single sideband or double sideband, you should consider the noise figure of single sideband, either single sideband or the double sideband. Another important parameter of the mixer is a port to port isolation, because there are a 3 port RF, LO and IF, and all has a different frequency and different amplitude. So, it is very important that how the one of the port, other port is how isolated, or how the signal is going fed through to the other part of the ports. So, if we can divide the various isolation, the important is the LO to IF. Now, always the LO amplitude is high, because we need to switch. Now, some unwanted LO signal appears at the IF port. So, that if there is an unwanted signal which is appearing at the IF, that is denoted by this, then it can desensitize the IF output if it is not properly filtered out, and it can be removed by using a baseband filter. So, LO to IF feed through, it will have a very high amplitude, and it should be properly filtered out, so that there is a other receiver component will not desensitize. LO to RF feed through. This is also very important. It will cause, because there is a LNA and then mixer. So, this will unwanted radiation will occur into the LNA, and another problem of DC offset will also generate because of this, because the same signal, if it will come back. So, this is a RF signal, LO signal, and if it will come back, and if you have a direct conversion receiver, at that time your LO will mix with the same signal, and it will generate a very high DC offset, and that high DC offset might change the operating point of your other receiver uh, components. So, it is better to have a good LO to RF isolation. Then RF to IF isolation. So, if some of the RF signal is feeding through to the IF, then it will have a even order intermodulation in the upcoming stages. Though the RF amplitude is not high, but there is a possibility that if you are near to the base station, at that time the RF signal is a high, and you if it is feeding through to the IF, your other frequency, other components might have a distortion. So, it is better, it can cause a even order intermodulation also in the incoming stage of the receiver. The final is RF to LO isolation. It can cause the injection pulling. So, we already have seen that if this signal is going back to the LO, and while discussing the transmitter, we have seen that how the injection pull happen, and it can change the oscillation frequency and also add the more phase noise. So, that is also needs to be isolated. So, RF to LO isolation, LO to IF, RF to IF, all needs to be uh, filtered out. So, there should be high isolation in the mixer. We will discuss more about the parameters and the mixer in the next class. Thank you.